All right, now we need to talk just a little bit about rotational inertia and rolling objects. And if we've got a rolling object, e.g. a ball, and it's rolling down a slope, if we know how to do the vector diagrams, we know that the net force acting on that ball is going to be equal to mg sine theta. Same for all objects, whether it be a box, a ball, whatever. And that's what makes things flow down the slope. As sine of theta, theta being that angle, as theta gets up to be 90 degrees or 1, then it's just the net force acting as mg, and it's a vertical force with an acceleration of g. So the thing is that when an object rolls, it builds up some kinetic energy, rotational kinetic energy, 1/2 I omega squared. And so for a certain distance that it falls, it loses potential energy, mgh. Now, we're used to saying mgh equals 1/2 mv squared. But now we've got to say mgh equals 1/2 mv squared plus 1/2 I omega squared. Now we can substitute that omega and get this, solve this formula for v, because as we know that omega equals v over r, r being the radius of the object, and we could solve that. And what we end up finding out when we do that one there is that and I think we'll probably go through this one in class, but we find out that the v equals the square root of 10gh over 7. Now, what's this got to do with rotational inertia? Well, you see, the rotational inertia came right into that. Now, I think you'll see that the more energy gets used up in rotating the object, the smaller amount there's going to be in the linear kinetic energy. So the bigger the I, the slower the object's going to roll down that hill. Okay, so bigger I means that implies less acceleration. And I is totally dependent on mass distribution. So if you had an object, the more mass you put out at a greater radius, the bigger the I, it's going to roll more slowly. And I'll show you this. We'll do a practical demo on it. But a solid ball, whether it be small or big, has the same I. So this is where we get that idea that similar shaped objects will roll at the same speed, because they have the same I. So similar shaped objects roll at the same rate. So same I, the same proportion of energy goes in to the rotational inertia, and so we're going to have the same amount of acceleration. This is an important thing.